The Open Shortest Path First, OSPF, version 2 protocols were defined in RFC 2328 as an interior gateway protocol for routing information within a single autonomous system. OSPF protocol was developed in order to solve the problem of large-scale routing and to introduce a high-functionality, non-proprietary interior gateway protocol for the TCP/IP protocol family. The OSPF protocol is a link-state routing protocol that removed the Bellman-Ford vector-based algorithms used in traditional internet routing protocols such as RIP. OSPF has introduced new concepts such as authentication of a routing update, VLSM, route summarization, etc. Open Standard Protocol. Administrative distance is 110. Classless Protocol. Metric used here is cost. Cost equals 10 raised to 8 BW in bits per second. Uses Dijkstra algorithm to calculate shortest path. Updates are sent through multicast address 224.0.0.5. Unlimited hop count. Triggered updates. Fast convergence. Hierarchical design with multiple area design is possible. 65,535 area we can create. Neighbors are made here before sending updates to anyone. Hello packet interval timer is 10 second. Hello packet will be containing router E, area ID, hello interval, dead interval, and authentication. Dead interval timer is 40 seconds. Area 0 is called backbone area. This support equal cost path load balancing. By default it will do load balancing on 4 equal cost path, but OSPF can do load balancing on 16 equal cost path. RIP can do equal cost path load balancing on 6 equal cost path, but by default TRIP will do load balancing on 4 equal cost path. Router E. Each router in an OSPF network needs a unique ID. This must be unique not just within an area, but within an entire OSPF network. The ID is used to provide a unique identity to the OSPF router. Router ID selection is based on following criteria. 1. If loopback interface is configured on router, then highest active loopback interface IP address will become router ID for that particular router. 2. If loopback interface is not configured on router, then router will select highest interface IP address as router ID of that router. Dr. NVDR router selection in OSPF. An OSPF router will not form adjacencies to just any router. Instead, a client-server design is implemented in OSPF on each broadcast segment. For each multi-access broadcast segment, such as Ethernet, there is Dr. and a BDR as well as other OSPF routers, called druthers. Dr. designated router. BDR, backup designated router. Dr. and BDR selection in OSPF starts under following two topology. 1. Broadcast multi-access, BMA. 2. Non-broadcast multi-access, NBMA. Dr. and BDR is just like server-client environment. There will be one backup server that is named here as BDR and main server is named here as DR, and other all clients are named as druthers. If any link goes down or up on druther router, then druther router will not inform changes directly to all routers. Druther router will inform that changes to Dr. and BDR router, and then Dr. router will inform the same change to other druthers router. Selection of Dr. and BDR router. Router has interface OSPF priority which is set to 1 by default. We can increase OSPF priority from range 1 to 255. Among all the routers, the router which has highest priority assigned to its interface will become Dr. router, and the router who has second best highest interface priority, it will become BDR router, and others will become Dr. other.
So click on router 1 and go to CLI and press enter. Type enable to go to privilege mode. Type configure terminal to go to global configuration mode. Type router OSPF 30. Now type network 192.168.0.1. Type 0.0.0.0 as wildcard bits. Remember, when we configure only one IP, we use 0.0.0.0 as wildcard bits, and when we configure networks, we have to solve the wildcard bits. Then type area 1. Type network 192.168.0.173. Type 0.0.0.0 as wildcard bits and type area 0. Close the window, click on router 2 and go to CLI. Press enter. Type enable to go to privilege mode. Type configure terminal to go to global configuration mode. Type router OSPF 30. Now type network 192.168.0.129 0.0.0.0 as wildcard bits and then area 0. Now type network 192.168.0.174 0.0.0.0 as wildcard bits, then type area 0. Type network 192.168.0.177 0.0.0.0 as wildcard bits and type area 0. Type exit. Again type exit and save it with the right command. Close the window, click on router 3 and go to CLI. Press enter. Type enable to go to privilege mode. Type configure terminal to go to global configuration mode. Type router OSPF 30. Now type network 192.168.0.178 0.0.0.0 as wildcard bits, then area 0. Type network 192.168.0.161 0.0.0.0 as wildcard bits and area 2. Now type network 192.168.0.181 0.0.0.0 as wildcard bits and type area 2. Type exit. Again type exit and save it with the right command. Close the window, click on router 4 and go to CLI. Press enter. Type enable to go to privilege mode. Type configure terminal to go to global configuration mode. Type router OSPF 30. Type network 192.168.0.169 0.0.0.0 as wildcard bits, then type area 2. Type network 192.168.0.182 0.0.0.0 as wildcard bits, then type area 2. Type exit. Again type exit and save it with the right command. Verify them. Open router 1 on privilege mode. Type show IP root. You can see that connected networks. Also there is OIA, which means OSPF inter area. Also there is O, which means OSPF. Check the AD value and matrix. Now open router 2. Type show IP root. You can see that connected network as well as OIA root, which means OSPF inter area. Now open router 3. Type show IP root. You can see that connected network as well as OIA root. Also there is O, which means OSPF. Now open router 4. Type show IP root. You can see that connected networks, which is denoted by C, and also OIA, which means OSPF inter area, and O, which means OSPF. Now open any PC, then verify that PCs are communicate with each other or not. Go to desktop, then go to CMD and type IP address. Ping 192.168.0.4. Here you can see that replies are coming from that PC. That means our configuration is successful.